goes like the Schwarzschild radius to the power d minus 3. The entropy goes like Schwarzschild radius to the power d minus 2, like the area. And so if we plot the entropy as a function of the mass, we get a curve roughly like that. Okay, on the other hand, we want to compare that to free string. So a free string has a mass which is of the form 1 over ls, so that's related to spring tension times some oscillator number, and an entropy which is proportional to, again, the square root of the oscillator number. The prefactor depends on what string we're considering, whether it's type 2, heterotic, etc. And the ratio between these two is m to s over m is some number which is by definition called the inverse hexagonal temperature. Okay.
So maybe I can ask a really stupid question. What is n here?
Yeah. So sorry. So we have a string wall-sheet, and let's say we have it on a circle of radius 2 pi. So we write all the normal modes of oscillation of the string. They are related to modes of a free field that moves on this circle. Their energies are quantized, the integer units. And n is the total energy of, let's say, the left or the right movers. So it's the sum of the occupation number of each of these bosons times n, and sum over all the n's. So somehow. And so when you quantize the string, you find that its mass is proportional to the square root of that number. Yeah. But all that we need to know, if you haven't seen these formulas before, is that when you have a highly excited string, the ratio between the entropy and the mass goes to a constant. And this implies that if we consider the string at finite temperature, and we consider the partition function S, right? So we're supposed to sum over all the, let's say it's a single string, we're supposed to sum over all possible states. This sum will diverge if beta is less than beta h. And so for that reason, this is called the maximal temperature. So 1 over beta h is the maximum temperature. But okay, so that temperature is important. Now, this implies that the entropy of the string, so let me write the strings, will have has a linear entropy, and at some point will cross the entropy of the black hole. So for a given mass, the black hole is more entropic for very large mass, and the string is more entropic than the black hole. So you might think that if we follow in the most entropic configuration, at some point the black hole will turn into string. Now, this argument is not really correct because we can only trust the black hole for very high temperatures, so very high inverse temperatures. So when the beta, which is proportional to the Schwarzschild radius, is much bigger than the string length. And similarly, we can only trust the entropy of the string when the mass is small enough so that it doesn't form a black hole.
Well, that thing that looks like a pie is an R.
This one? Yeah. Okay. Sorry. Well,
No, it's just
I thought that was a very clear R, so we're going to have a lot of trouble. And one more thing I will say about the string. So this is a highly excited string. The size of these string states, you can think of these string states as roughly a random walk of the string that has some tension T. So the total mass of the string is basically the well, it's the number of steps that you have in the random walk. And so the size will be proportional to the square root of the number of steps. So it's proportional to the square root of m. So it's proportional. The size is proportional to the fourth root of m. Okay. So as you start exciting the string more and more, this free string picture, so the string gets larger and larger. You can nevertheless here, even though we could extrapolate these two formulas and ask where you would expect them to meet, and they meet when the two masses and entropies are the same. So the vertical side here is the entropy, and that happens well at the value mass, which goes like 1/g Newton. And the important part is that the size of the system at this point is of order ls. So it happens at threshold radius, which is of order ls. And the fact that it happens here comes simply from the fact that if we take the ratio of these two quantities, so s over m will be proportional to rs. And so if the two are equal, then this ratio should be equal to this beta h. Beta h is of order string length, I guess they could mention it.
Why doesn't this n to the quarter like appear in where you might expect that? I mean, you might very naively have thought that the transition occurs when the would-be size of the black hole is this string scale.
Yeah.
But this picture is telling that it's actually growing a little bit more than that.
Yeah, that's right. So things don't match. So at this level.
Oh, okay.
Yeah. So So here, when you have this very big size, weak coupling, the string will be much bigger than the black hole. So, but anyway, just this crossing of the entropy suggested there might be something. Now, another thing that happens is that if you consider a black hole, that's the black hole, and if the black hole has a Hawking atmosphere, and in particular, it has some atmosphere of strings that sort of end at the horizon, and as the black hole becomes smaller and smaller, this temperature becomes higher, and you will expect these strings to grow, and maybe there is some transition where it's mostly strings and very little black hole. So this is all very qualitative, but it suggests that there might be some kind of transition like this, and the question is whether there is, and why do we care? The first question is, so general relativity is a theory of gravity, and we find a simple solution. The Schwarzschild solution was one of the first solutions was found, and you can ask in classical string theory, what is that solution? And in particular, what happens with the black hole when it becomes very small for the string size? Now that's one question, but I think a more interesting reason to care about this is that in one of the pictures, when if there was some smooth transition, I will try to say why we might expect a smooth transition. In one picture, the black hole picture, there is an interior of the black hole. And in the string picture, the microstates of the configurations are manifest. You could wonder whether if there was a continuous transition, maybe you could start seeing these two features in one way or another. So this is one reason why you might care about this. Now, in order to make this a little more concrete, it's necessary, it's useful, and well, it's important for what we were discussing, to note that there is an interesting solution that was proposed by Horowitz and Polczewski, which describes a self-gravitating string. I will spend a lot of time discussing the solution. First, let me just say what the picture will be. And this solution exists in various dimensions, but the best situation for us will be in 4 dimensions, 4 space-time dimensions. And the idea is that we start with this free string picture, and we include the leading effects of gravity. So the leading effects of gravity, we form a kind of string star where the string is oscillating, is at high temperatures, and there is some gravitational potential that binds the string, holds it together. And we will see that when we include this, for example, the the size of the object starts getting smaller as we increase the mass. You get smaller, and then it gets to reorder of string size when that approximation breaks down. And another interesting aspect, as we'll discuss in more detail, is that we can think of this solution as a classical solution in string theory, as a certain conformal field theory. And for that reason, then the reason of the transition we're going to be asking is whether there's a transition between this self-gravitating string and the black hole. Okay. So let me discuss this solution in more detail. And so the plan of the talk is I will review this solution in some detail, and then we'll discuss how it is connected with the black hole. And the bottom line is that for some string theories, it seems to be continuously connected to the black hole, and for some others, it doesn't. Okay, so in order to discuss this solution, it's useful to think about string theory at finite temperature. Let me say a few words about string theory at finite temperature. So we think about the canonical ensemble, where we take space-time and we compactify it on a circle of radius beta. Okay. Not beta h, just beta. And we'll be always throughout this talk talking about the classical string theory. So we're not going to worry about one loop effects and so on. So here we can have a string winding mode, so that winds around the Euclidean circle. And this mode will have a mass naively. So it's a mass which is proportional to is equal to the string tension times beta. Okay. But but there's also correction due to the quantum fluctuations along the string, so some kind of negative Casimir energy, which would subtract something, so some number from here, which is proportional to 1 over beta. And using the usual quantization of the string, you can write even a more precise formula where this is equal to well, t times beta h, where beta h is some number, exactly what it is, which was that higher temperature we mentioned before. So when the circle, the Euclidean circle, gets to be of order this number, this mode, which in general is massive, becomes massless. Okay? And if you go beyond that, it becomes tachyonic. So there, that's a manifestation, if you wish, of this maximal temperature that we have. Very good. So you can go ahead and compute this number. So for example, beta h is equal to 2 pi square root of 2 times the string length for the case of the type 2 string. We will also discuss the heterotic string, and in the heterotic string, we have a different number of left movers and right movers along the string wall sheet, and therefore the Casimir energies for the left movers and the right movers will actually be different, and we will have some net amount of momentum along the string. So not only the string has winding in the Euclidean time direction, but it also has some momentum. And it turns out that it has a half unit of momentum through this calculation of the Casimir energy. That's what it works out to be. And I guess this fact that it has a half unit of momentum, I think, was first discussed in a paper by Attic and Witten, who studied this problem.
I'm sorry to interrupt you. So T beta H is just a number, right? Is that right? T is the tension. T is the
yeah. Well, this is some. There's a 1 over alpha prime here.
Right. And is that like in the bosonic string? Is that the same as what the mass of the tachyon would have been, or?
Yes. Yes.
It's just that when you're on the thermal circle, you're breaking.
This
anyway.
is
That's basically the tachyon.
Just a tachyon.
Right.
Yeah. So for the tach 2, it's just tachyon. Yeah. And similar for all these various. So this is sometimes called the thermal tachyon. I didn't use so much this. I'm going to use the word binding mode because it's we're going to be interested in beta bigger than beta h, so it will never be tachyonic. And So in the heterotic case, the formula for the mass squared has a term proportional to, well, maybe as a term proportional to, but instead of beta, let me define R, which is beta over 2 pi, to eliminate some function of 2 pi. Then it has a term proportional to this, and then there is a term that goes like 1 over 4R squared. Well, maybe I shouldn't say. Well, so it has a slightly more complicated dependence, minus the same thing with RH. The precise formula is not so important. What is important is that it carries this 1/2 unit of momentum. And then it has some value, this RH has some value that you can write down. Its precise value is not important, but it's just only that there is some concrete value that it has that you can calculate. And again, when R goes to RH, there is a massless mode. There is a massless mode. Okay, so that's some background. That's when we neglect the effects of gravity or any other massless fields that we will have. And now we will consider the effect of massless fields. So we'll consider that same setup, and we're going to dimensionally reduce on the circle and consider a theory in 1 less dimension. So if we started with a theory in d dimensions, now we're going to go to d dimensions. So little d is the number of spatial dimensions that we will have. So after reducing
But for this half momentum, it's not really necessary to go the heterotic string, right? I could also take type 2b and put like 1 oscillator for the left movers and the right movers or something.
Yeah, so in the type 2, you would not allow any particle to have 1/2 unit. They will all have integer units. Oh. So the half unit is something special about the heterotic. I'll not try to justify it a little further now. Yeah. And maybe I just mentioned that there's something confusing that it has a half unit of momentum because it looks like it's breaking the time translation symmetry that we wouldn't expect. If we had a web of this tachyon, we wouldn't expect it to break the time translation symmetry. And this is a point we haven't fully understood, but we think that there is an unbroken symmetry, which is a combination of time translation and winding, and that should be viewed as the proper time translation symmetry, translating by the Hamiltonian of space-time theory. But it's something that we haven't fully understood. But that's what I would say for now about this. Okay, so we can write down, so Horowitz and Polczycki wrote down this action, which is an action in d dimensions. So we can have a d-dimensional dilaton, the usual string type action with graviton and dilaton fields. Okay, so this is standard, but now we'll have to include this tachyon field, which we're going to call chi. So there's a term gradient of chi squared. And it will have some mass squared, and the mass square will depend on the radius of the internal dimension. So it will depend on the value of the metric in the Euclidean time direction times chi squared. Yeah, so, and in addition, we also have, I should have written here. So this is the d-dimensional curvature. There is one more massless field that we have, which actually will be important for us, which we're going to call phi. And phi will be basically in the Euclidean time direction. We are going to write the metric as, well, the metric at infinity, which will be given in terms of beta squared times e to the 2 phi. So
that's like the radian of this circle.
And so this ends up being a function of this phi. Yeah.
It's the radian of the circle.
It's the radian. So we have this, it's just the radius of this circle. It's the mode that deforms the radius of the circle. And so that's the action that we'll have. Now we are interested in this problem in principle. So here you see chi interacts with all the massless fields that we have, and the main point will be that we are going to be interested in a situation where beta minus beta h is much less than ls. So this is the crucial approximation for everything that we will say now about this Horowitz-Polchinski solution. So they're working on this approximation. And in this approximation, this mass square term is very small. So this mass square term sets the scale of the solution. And we would expect here that, so notice that there are some couplings to the massless fields that will go through m squared. So for example, the coupling to, let's say, spatial component of the metric here will be proportional to m squared, because we expect that the gradients are also proportional to m squared, and so on. So there are a bunch of couplings like that, which are suppressed at low energies. But there is one special coupling that is not suppressed, which is what you get by expanding this mass squared. So the mass squared has a factor like this, which once we put phi will depend on the radius of the circle. And then we can expand in phi, and there will be a term that is a zero, which is what we have at phi equal to 0, which is just the mass square that it will have very far away. And yeah, perhaps I should have mentioned that the kind of solution we are looking at will be a solution where chi is localized. So there is a localized lamp of vacuum that is localized in space. So and so the mass at infinity is the mass that is given by well, this at infinity, and at infinity phi will go to 0. And then there is a term that we call kappa times phi. And kappa is just the, well, it depends on the higher on temperature and so on. Something depends on some constants of the problem. They're not important. And it just represents the first order term in the expansion. But notice that this term is not proportional to m squared. It just involves some large coefficient, which is Horowitz string scale. So this is basically the largest interaction that we have in the system. And that's therefore the only interaction we're going to keep. And so we're going to approximate. So we think that phi, this phi will be the only field that will be excited. So the full action will just be this plus gradient of chi squared plus m squared plus kappa phi times chi squared. Okay. So all the other fields will be set to 0. So in particular, the d-dimensional dilaton and the d-dimensional metric. The d-dimensional metric is going to be flat, and the d-dimensional dilaton is going to be set to 0.
So Juan, so this phi is mediating some attractive interaction between the chi's, but you don't care about gravity anymore.
Exactly. So this this phi is, roughly speaking, the Newtonian potential. So it's mediates that Newtonian force. I say it roughly because there is also a dilaton force. The capital D-dimensional dilaton is non-zero, so that also is included in phi. But it's just a combination of the fields.
But literally gravity is gone because it's not.
The D-dimensional, there is no D-dimensional graviton, but of course phi is a mode of the capital D-dimensional gravity. So and in the D-dimensional picture where we have the picture of this.
Right. Oh yeah, I got it.
Newtonian force essentially.
Great. Yeah.
Very good. So this is the action we're going to consider. And then it leads to some simple equations of motion that you can write down. And those equations can also be solved. And you find some solution where, well, first of all, before discussing the solution, I should mention that in these equations, you can scale out this m infinity, so it scales out of all the equations. And so the equations that you get are essentially only one equation for dimensionless quantities. There's only one equation that you need to solve, and that gives you the profile of the of chi, so as a function of r. There is some profile for chi that you can find. And there is also similarly a profile for the gravitational potential. Okay, so
I'm a little bit confused. So
Yes.
where is the Hagedorn beta 8? Where is what value of phi does it correspond to?
Okay, so we have that the m squared at infinity, which is this parameter in the action, involves beta minus beta h. Okay. Squared, but well, it's linear in beta minus beta h. That's how it vanishes. And then beta h appears here and so on. But the important point is that beta minus beta h does not appear here. Okay. So phi represents a dimensionless deviation from. I had written here the value of the metric. So it's the temperature times.
So that's why I'm confused. So if it's infinity or lower temperature, the Hagedorn,
Yes.
phi fluctuates. It would be a region where you are above the transition.
Right, indeed. So this is the. So initially we had a circle which had constant radius. Let's say this is r equal to 0. So now we have some tachyon lamp here.
What's R?
R is the radial direction. This is vertically symmetric. So I'm here at Roman chess. Fine. So indeed, you will find that it shrinks a little bit, only very little. So I'm exaggerating here the amount that it shrunk. And the field chi will indeed be tachyonic in this region. But the solution is perfectly small. So it's just slightly, the mass, the total mass square, so the sum of these two things is negative to the center of the solution. Okay.
But everything is stable because there's gradients. There's spatial gradients, I guess.
Yeah. So we have a spatial gradient. So this is the solution. The solution, the full solution has actually a negative mode. But well, the black hole also has a negative mode. So that we just Jewish. Now there is one interpretation of this solution which is similar to the interpretation that Edward gave of the black hole as a decay mode. So you could think that here I was talking as if the circle is a thermal circle, but you could think it's a spatial circle with antiperiodic boundary conditions. And then this can be viewed as a kind of bounce solution that mediates the decay into some configuration where the circle is shrinking and the tachyon is becoming larger. So you can also have that interpretation. And from that point of view, it's also natural that they should have a negative mode because that's what's happening.
The interpretation string theory that, like in Antiquiten, if I remember correctly, there was the interpretation that at the Hagedorn temperature there's a non-zero partition function coming in. So it's also here your interpretation.
Yeah. So Attica and Witten, what they said was something like the following. So imagine you were to calculate the potential as a function of the winding mode. So if we are at beta bigger than beta h, we know that the potential is quadratic and positive. Right? But then they said, well, if we integrate out massless fields, then that would typically induce, okay. We have this positive potential, but if we want to explore the potential further away, we need to know about the interactions of the tachyon. So naively, if you were naive, the first thing you would say is that, well, we just compute the tachyon self-interactions and we see whether it's positive or not. But actually, you have to be a little more sophisticated and realize that you could be exchanging massless fields, and you have to integrate out the effects of the massless fields. And that will give you a potential force which is negative. So they had a picture essentially like this for the potential. That's roughly the potential you would expect for a uniform tachyon field configuration. And you can view this type of solution as the solution that is giving you a kind of bounce or tunneling between this point and between this false vacuum and something that we want to provide situation. I don't know if I'm answering your question. Yeah, so it's intimately related to the Attic-Witten and these massless fields that you're exchanging. Is this field phi?
So where is this the ordinary negative mode of gravity or the ordinary negative mode of the black hole? Is it included or is that in the part?
Well, I'm not sure. So we have this action. you can consider a solution and then consider small off-shell fluctuations. And among the off-shell fluctuations, there is one negative fluctuation. We basically found one negative fluctuation with that's. Yeah, I don't think we demonstrated that that was the only one, but we found one. We expected only one.
How would you get anti-periodic boundary conditions in a spatial circle in string theory? Is there some like dynamic object that could create this?
Yeah, so you just have the choice of which boundary conditions you put on the fermions.
Yeah.
So you could choose them to be periodic or anti-periodic.
Yeah.
It's part of the choice of the background spacetime, if you wish.
Yeah.
So if we are doing the thermal problem,
No, I was meaning just normally in string theory when you think you're choosing some boundary conditions or something, then it turns out to be something dynamical like a deep brain or something like that. But maybe in this case, it really is.
yeah. So in this case, yeah, you just choose it. And, right. Okay. So yeah, usually people consider convectivity periodic boundary conditions. Okay, so that's. I think I'm going very slowly. So speed up a little bit more. Well, one interesting feature of this solution is that it has a non-zero entropy. So it's a classical solution, and if you calculate 1 minus beta dd beta, so the usual formula for the entropy times the logarithm of the partition function or minus the action, then there is usually an argument that tells you that the entropy should be 0 in any gravity solution, which is that there is an overall factor of beta here coming from the dimensional reduction. And that when you pass this derivative through, you end up with a derivative of the Lagrangian with respect to beta. And the Lagrangian does not depend exclusively on beta. Okay. And the derivatives of all the fields with respect to beta, all that part cancels out because you can use equations of motion. So all you're left with is the derivative with respect to beta of the Lagrangian. Normally, the Lagrangian doesn't depend on beta. So here it depends on beta through this term. And because of that, you get that there is a classical entropy proportional to chi squared. Okay, so that's an interesting feature of this. Of course, the black hole is another example of a classical solution that has a non-zero entropy, and it has a non-zero entropy for a different reason, which is that the circle shrinks. Okay. So it's okay, this is a solution, and the Lorentzian interpretation of this solution is that it represents a hot gaseous springs self-gravitating sort of string stars. And here we are solving the equations for the star. In fact, exactly the same equations that you get from this action are also obtained if you consider a Boson star. So just a bunch of massive particles forming a Bose-Einstein condensate, self-gravitating. You'll find it exactly the same equation. With a different interpretation. So the size of the solution is, as we said, proportional to 1 over this. So it's proportional to 1 over the square root of beta minus beta h. And you can also calculate the mass, and it's also proportional to 1 over square root of g Newton times the mass. So as the mass increases, the size decreases. And so now we can draw a little diagram. So it's a function of the mass, the various states that we've been discussing. So we discussed the free string state that has, sorry, I'm drawing here the size. We saw that the size was growing, so it was growing like some power of, well, maybe m to the 1/2. Then there is a region we don't understand. And now then we have the HP solution. It has a size that decreases. Then there is a region we don't understand. And finally, we have the black hole solution where the size increases as the mass increases. Okay. So all these transition regions we don't understand. Now here, the reason that the Horowitz-Polchinski solution breaks down in this direction is that this is a classical solution. You can compute the effects of quantum fluctuations. So how much the field fluctuates around the classical action. And you find that the fields fluctuate a lot compared to the values of the field in this region. So here we are expecting to find the transition to the free string picture. But most of the rest of our discussion on our paper was centering on this transition, the transition between this Horowitz-Koszynski solution, which is a classical solution of string theory, and the black hole solution, which is also a classical solution in this regime. So we can trust, here we can trust the black hole solution when beta is much bigger than LS. Here we can trust it, in that other regime, complementary regime. Okay, very good.
Want to ask quickly, is the shrinking that you get between the first and the second transition enough to sort of make it so the previous n to the quarter?
Yeah.
Just at the transition?
Yeah, this all the parametric scalings match between these two regions. So, yes. So now this discussion leads you to suspect that maybe in the full string theory they are continuously connected there. What that means is that as conformal field theories or solutions of classical string theory, they are continuously connected. So that we have a one parameter family of solutions. So the conjecture or the question is whether we have a conformal field theory with a one parameter family of conformal field theories that depends on beta, the size of at infinity. And as we vary beta between beta h and infinity, we interpolate between the two. That's the question. Now, both have non-zero entropy, and both also break the winding symmetry. Might not be trivial why the black hole breaks the winding symmetry, but if you have a string that is wound here, you can sort of slip out through the horizon. And in fact, the wave of the winding mode will decrease like e to the minus r times, of course, in infinity. So it has some decreasing wave that you can sort of estimate, not precisely. Okay, so both have similar symmetries, so they might be related. Okay. Now, if you have this hypothesis, then one way you could try to check this hypothesis is to compute perhaps some invariant of the field theory, so something that does not depend on continuous parameters, and that way you could check it. So I remind you that in the type 2 solution, type 2 string theory, we have a 1,1 supersymmetric Walsh theory. And in the heterotic case, we have a 0,1 supersymmetric Walsh theory. And so we can use this supersymmetry to compute some invariants to see what happens. And a simple invariant is the so-called supersymmetric index or Witten index, where we take trace minus 1 to the f times e to the minus beta tilde h. So on the Walsh theory, so we consider the Walsh theory, for example, on a cylinder, and we calculate this quantity. Beta tilde is some Walsh temperature, has nothing to do with beta. Okay. And so we can calculate this, and the argument is that this is first of all independent of this beta tilde, and you can think of this as counting the taking the trace of minus 1 to the f over the ground states over the Ramon ground states of the system. And in models, so we can calculate then this index for the black hole case here in the region where beta is much bigger than LS. Maybe I should perhaps have said that. Well, probably people have heard about this index before, so I don't need to explain why it is invariant. But this index, so that's not dependent.
Type 2, can you also have an S sector for one side?
No, so the index is here defined. When you consider this problem on the worldsheet, of course you could have the NS sector, but the index is an invariant when you consider the Ramon sector.
Because if you have two, if you have Ramon saying the right movers, can you have?
Oh yeah, for the heterotic.
No, heterotic there's no choice, but in type 2.
Yeah, you can do that. Yeah, that's the so-called elliptic genus. Yeah, you could consider that too. For what we're going to discuss, it's enough to consider this. Okay, so the point is that, well, let's consider first this case. Then the index is related to the Euler characteristic of the target space. And for the case of the Horowitz, so the Euler characteristic is the sum of differential forms with various, well, with the -1 to the degree of the differential form. That's the differential forms and spinors are related, and that's why you're essentially doing this. So, well, sorry. Okay, so in the case of the Euler characteristic, in the case of the Horowitz-Polchinski solution, the topology of space is just that of a circle, it's just that of flat space, and so we'll get equal to 0. And in the case of the black hole, we actually we can calculate that it's equal to 2. And well, in this case, well, there are various ways to see that it could be 2. So one is the formula for the Euler characteristic in terms of the curvature, but you can also see that in the case of the black hole, there are actually two normalizable two forms. One is the two form that is defined on a sphere. So take the volume form on the two sphere, and that is normalizable. And you can also have the dual of that, which is a two form that is localized here, and that is normalized. So you can find these two normalizable. And that then contributes this factor of 2 to the index. So we see that it is different. So we cannot have a continuous smooth interpolation between these two solutions.
Say again, what is the precise solution? Black hole solution? Like Schwarzschild?
Yeah. We're considering Schwarzschild. So we're all.
That's not critical.
A four-dimensional Schwarzschild solution.
But then, to make it a string solution, you have to add something.
Yeah, so the four-dimensional Schwarzschild solution is a solution when beta is much bigger than Ls, okay? And then there are some corrections which are powers of alpha prime, right?
Lawrence is just saying that you need an additional system of C hat equals 6.
Ah, sorry. Oh, sorry. Yes. Sorry. Yeah. So throughout this discussion, we're imagining we have the CFT that has a C hat equal to D, okay, and times another CFT that has a central charge, which is 10 minus D. Okay? And this one is always left untouched, and we are just following what the conformal field theory describes the D dimensions is doing.
A little bit confused with this because like summing over the GSO, doing the GSO projection mixes the two up.
Yes, but here, so here what we are saying is, well, we are going to construct the full theory by taking a CFT, this CFT in D dimensions, whose target space is a black hole, and we consider that CFT before we do the GSO projection. Of course, it should have the chiral symmetry necessary to have the to do the GSO projection. And then we're going to take the product with some other CFT. So that's the approach we are taking. So we are considering purely this problem in D dimensions. And both solutions in the at least extreme limits, they can be viewed as purely within D dimensions, and also the corrections to these solutions can also be viewed just in D dimensions.
Do we think that this internal CFT is the same for both solutions?
Yes. Sorry, I should have explained this point earlier. So thanks for asking me. So yeah, we're imagining we have this internal CFT which keeps it's always fixed, which has been an internal torus, right? The torus of dimension 10 minus D. And then we are considering a space-time part, and we are focusing on the space-time conformal field theory. Sorry.
Change the answer, like if these two theories can be related, if the kernel CFT to be different between them?
Yeah, you would have to do a separate analysis. So the analysis as we did is for this particular setup. But in the context of string theory, we expect the problem to factorize in this way. So the fact that given that we started with a nonlinear sigma model in d dimensions, if we consider, for example, the alpha prime correction, so we'll modify that and eventually should produce an exact solution of string theory purely in d dimensions. Or an exact solution, an exact CFT in d dimensions. And then we take a tensor times some other CFT. Okay. Okay, so now,
do you have this discrepancy for any D or not?
yeah, so yeah, we have this discrepancy for any D. The Horowitz-Porzingski solution doesn't exist in all D. That's one subtlety. The second is that when D is odd, actually the index vanishes in both cases, but you can fix that up by adding here a reflection in one of the axes, and then the index will be non-vanishing. So, and this is also an index because this is a global symmetry. Okay, so very good. So now we go to the in the heterotic case. So the index related to the Ramon ground states. So in that case, in this particular case that we discussed, the Ramon ground states are roughly like forms because they are essentially like the Ramon field strengths, essentially, where you can a small variation of those. While in the heterotic case, the Ramon ground states will be more like spacetime fermions. So the index is related to the index of the Dirac operator in the target space. And that is zero in both cases. The 0-1 theory, the index is zero in both situations. Okay.
Now, actually, I have one more question. Is it usually the argument that the index is invariant only works for complex CFTs, and for non-complex CFTs there can be subtleties?
Yes.
So is that clear?
Yes. Well, yeah, indeed, that's a subtlety. Now, yeah, here the idea is that you could imagine either compactifying far away and thinking, well, here the idea is that at infinity you have basically flat space, so very simple CFT, and nothing is basically changing in that region. So you would expect there to be a problem. Now you could imagine a theory which is not exactly conformal, but where you compactify that region, and the index now it will be well defined in that non-conformal theory. And if the conformal theories were connected, then the index should be well defined and the same in both cases.
In this solution, we have a region in the phase, which is roughly trying to be in the other phase.
Yes.
Right. So what's the scale there? Is it large enough that you can actually get some information about the other phase?
Not really. I mean, here in solution, the tachyon condensate is very small. So in the regime that you can trust, the tachyon condensate is small.
So this does not give you a glimpse of what's going on the other phase?
Not really. But if you wish it, you can also view it as a bubble nucleation where you nucleate some bubble, which then will continue to grow. The other phase is not. The other phase is suspected to be very far away, right? At least, so it's this picture that we discussed in the context of when we were talking about the Attic-Whitney paper. So the other phase is well deep there, where the tachyon becomes infinite, or very large compared, at least compared to the one. Okay, so now so this is just some first indication. So now there is a construction that is useful. A useful tool is consider linear sigma models. this is a technique that Edward introduced to analyze mainly 2,2 theories, but we can also apply it for this problem. And so in this 0-1 situation, the idea is to start from a free theory, so a theory that has some simple behavior, and then you add some potential, and you have a non-conformal theory that in the infrared flows to the CFT that you're interested in. So in this case, the idea is to start in a theory in t+1 dimensions, where we have two vectors, x is x1 and x2, and then we have some vector y, which lives in Rd, so y1, y in D. Okay. And then what we're going to do is we're going to add to the theory a kind of superpotential coupling, which so this is an integral over the superspace. So there is only one theta variable, so it's a theta plus variable. And then there is a lambda superfield, and then some superpotential, which is a function of the superfields. Well, I'm going to denote them with the same letter, but superfields x and y. And so the idea will be to choose a suitable function. Now, if we start with this superfield action, so lambda is a superfield which essentially contains a left moving fermion, so that's in the non-supersymmetric direction, plus some auxiliary field we can call D. And then after we integrate this auxiliary field, after we integrate the auxiliary field, we get the bosonic potential, which is of the form d square x times w squared, where w is the function we get here. So we can choose some function w, which make sure I don't erase it. So we choose this particular function w, then when we float to the infrared, we can consider the supersymmetric vacua, and this supersymmetric vacua will exist when w is equal to 0. And so we set that to 0. We get that x squared is equal to b plus c over y squared plus a. Okay. I think I want a minus here. Maybe I want a plus here. But okay. So what we see is that when y goes to infinity, this circle, this forms a circle of radius square root of p. Okay. And then when y squared becomes very small, if let's say c is very small, then when y squared is very small, this is a circle slightly smaller. Okay, so that's okay. So that's in the Horowitz-Polchinski situation. But let's say at y equal to 0, the radius of the circle is b minus c over a. And so depending on the sign of this, will be either in the Horowitz-Polchinski side or in the black hole side. So as we vary these parameters, we have something with the topology of one solution or the topology of the other solution.
So
Now the metric, yeah.
the black hole is the case where y can't change.
Yeah, that's right. So when y is equal to, so I'm here, this right-hand side, when y is 0, right, is equal to this. So therefore, when b minus c over a is bigger than 0, we are in the HP topology. And when b minus c over a is less than 0, we are has the black hole topology. So here we cannot go all the way to y equal to 0. We can only go to the value of y, where this quantity it becomes 0. So there the circle has shrunk to 0 size at the non-trivial value, a non-zero value y. Okay, so good. So then the idea is that we have this original linear sigma model, and we vary the parameters. Nothing special is happening when this is actually equal to 0, and therefore we expect that we have some smooth transition between the two. At least at the level of the before we flow to the infrared, we have a smooth transition between these values of parameters, and it's reasonable to think that when you flow to the infrared, you could also have a smooth transition. Now, it's not really a proof, because it could be that when you flow to the infrared, there is some infinite throat appearing or something weird happening. But there is no obvious reason why that should happen.
Can I ask, when you're on the Horus Polchinski side, as you, let's say, vary B, the low energy CFT is changing.
Yes.
Yes. But then if you go to the other side, as you vary B, is it always the same low energy CFT, because the black holes sort of be universal?
Yeah. So well, both solutions have the property that they are parameterized by just one scale, and they scale in a simple way. Yeah, regarding to your questions, part of your question is to ask how the parameters of the final solution, which is supposed to be only beta, depend on the parameters of this, which are three. There are three parameters here in this discussion. So the idea is that one combination of these parameters will be the parameter beta. So when you're in the black hole side, you will get different CFTs for different values of beta.
Oh, okay.
And they are not all the same. So in the gravity approximation, they are the same, but the alpha prime corrections are different. So there are further corrections. So in terms of the number of parameters, so there is one parameter in the CFT, right? Here we have three parameters, and the idea is that one of them is the one that we want. Okay, that should be a marginal deformation of the CFT. Then one of the parameters is supposed to be a relevant parameter that we will need to fine tune to get to the CFT. And the reason that we expect this is that both these two solutions have a negative mode, an off-shell negative mode. So that will manifest itself in the CFT as a relevant deformation, possible relevant deformation. So we'll need to fine tune some parameter. And since we have one left over, then we think, but it wasn't really proven, that this should be an irrelevant parameter. Okay. So the idea is that when you go to the zeros of this potential, you find some surface within this space. And there is some induced metric on that surface, but that induced metric does not give rise to conformal field theory. That induced metric will flow under the normalization group flow into a new metric, which will obey the proper equations and will be
How do A, B, and C flow under renormalization?
Yeah, so in the UV theory, both A, B, and so these parameters have logarithmic divergences, and they flow logarithmically in the
In which direction? Do they get towards or away from the transition point?
What happens is, remember.
Right, they are renormalized because it's 1, 0, or 0,
Yes,
1.
yes. Well, I guess you can see that there is a logarithmic divergence that grows with the cutoff. So B will behave like log of lambda with a positive coefficient. That's the B pair, right?
And C and A?
A is similar, and C goes quadratic. Good logarithm, product with the square of logarithm.
So this combination B minus CA, which direction does it flow? Well, in other words, can you start in the UV in one phase, but after running, you find yourself in the other phase?
Yeah, that will typically happen. So yes, in principle, yes, but what we have is that what matters is, I mean, there are these divergences, and then of course there is some renormalized value, right? And as you flow, you will have to adjust the parameters so that you end up in the right phase. I mean, it's all part of solving this problem. So there is not only so what we also care about in the end is about the space that we have in the deep infrared. That will depend on a complicated value of parameters because it will also include the flow of the metric. For example, yeah.
So if these parameters are in some sense irrelevant, then basically read off the answer from the branch. If they start growing,
So the relevance or irrelevance of these parameters comes at the not at this stage of finding how they behave in the deep UV, but this notation here was what these parameters are from the point of view of the infrared CFD, which will involve the flow of the metric and so on. Okay.
I actually have another question.
Yeah,
So
please.
if I just write, what is the space of X and Y look like?
Well,
And especially when
the space of X and Y is just R2, well, the UV theories are 2 plus 3. I'm not sure, perhaps that's not what you're asking.
right, but there's something interesting in the interior.
Well, this is the full space in the UV theory, it's just R2.
Right, but there's some region inside.
And then, yeah, that's right. There is some surface inside. There is some, so W equal to 0 defines a certain surface, right? So you have, I don't know, ID, and then there is some surface, right? That has a circle far away, and behaves in some way.
Right, and the region inside,
Yeah.
where this thing is,
Yeah.
is far from far space,
Yeah.
or flat space.
Yeah.
As you undergo the renormalization, does it shrink or does it expand?
Well, we don't know how this metric behaves when you flow from this surface to the infrared. We have not analyzed that.
The thing is that there are such models with non-compact ends. Imagine this
Yeah,
one.
yeah.
So maybe
Well, I think yeah. So there are situations, for example, have in mind something like the cigar, for example, where it has positive curvature, and then under flow it negative.
yeah, because either move this way or can move that way.
Yeah. So we move that way, and in the case of the cigar, that flow is related to the fact that you will have a varying space-time dilaton.
But there are situations where it's more dramatic. You have something that
Yeah.
say there's some region.
Yeah.
And by the time you run, this region expands and eats up the whole space.
Yeah. So
And then you end up with something which is completely big.
yeah, you could end up with nothing. But here we start with something that has the right topology, and we are making the hypothesis, but we definitely did not prove it. But this flows to the black hole. Right? For example, even at large radius, you can flow to the black hole. That we have not looked in detail at the equations to see how that happens. We're just assuming that it will. Okay. Okay, so I think I'm over time. So, well, you can consider the type 2 case. So that's the 1-1 sigma model. I guess I went too slowly, but if you do the 1-1 sigma model, then you can write a similar looking potential. Now we have 2 variables, 2 theta variables. And it's convenient to introduce a new superfield T. And then in this case, the equations for the vacua are similar. Well, instead of having y equal to 0, so we have an expression like this. So the derivative of this superpotential with respect to all the variables has to be 0. So in particular, the derivative with respect to P says that W should be 0. And then there are derivatives with respect to the other fields, which imply this quantity. That implies this equation. So one possible solution is to set W equal to 0 and P equal to 0. That then will set W equal to 0 and P equal to 0. And that then will reproduce the two branches that we discussed according to the signs that we're discussing here. But the new feature that happens is that when B means C over A is equal to 0, then a new branch, so this is still a possible solution, but a new branch appears where x is equal to y is equal to 0, and p is not 0. Okay, so it looks like a new branch opens up. That's in the classical theory, but it turns out that once you consider the quantum corrections, this new branch gets a superpotential. And in the end of the day, what happens is that I guess maybe I should continue drawing here, otherwise people. So what happens is that I'm going to present somewhat simplified pictures, but as a function of the sign of C minus AB, there is some region where some region where you have the Horowitz-Polchinski solution and some region where you have the Blackwell solution. And then there is a superpotential P, and this leads to the appearance of a new sort of massive vacuum. So along the P direction, there can be some massive vacuum. And what happens then is that if we so here we have two massive vacuum from this P branch plus the Horowitz-Polchinski solution. So what happens is that okay, let me first I'm going to quit. I'm out of time. So. Let me just summarize. So in other situations where there was similar transitions or similar CFTs, what was happening in the linear sigma model was that the new branch appears. And that sometimes in target space means perhaps a linear delta or something with some region of strong coupling. But in this case, classically, there is a new branch, but quantum mechanical in the sigma model, so after including quantum corrections, there is no new branch. And therefore, it says that the index should not be able to change. And in fact, the index does not change. And what happens is that the theory on this side has two branches. One is the branch where the target space is this Horowitz-Polchinski solution, and another branch which has two massive vacua. So this does not give rise to conformal field theory. So if you look only at the conformal field theory part, the index jumps. But if you look at the full theory, then the index does not jump. So a singularity that we are expected to find between, but we go between one and the other, has to do with the appearance of this extra massive vacuum. And we haven't fully understood what that means in the CFD. So it's a new way, it looks like it's a new way in which the CFD can become singular. So the only way I knew that the CFD could become singular is by developing a non-compact target space and perhaps a region where the dilaton becomes very, very large. And perhaps that happens here. It's not obvious how it happens, but it could be that that after you flow to the infrared, maybe some target space becomes very large and connects to these two massive vacuums. Okay, so that finishes this discussion.
Sorry, can I ask that? So what does it mean for space-time? Space-time is a disconnected piece. How should we think of these two vacuums?
Yeah, that's a good question. I don't know. So
well, the fluctuations around one of them look like one space-time, and the others look like a separate space-time.
But they have C hat equals 0 instead
Yeah.
of 4. So they don't make much sense to the string theory.
I also don't understand what it means to have a disconnected space-time. I don't know which question should be addressed first.
Should not think about it as super selection sectors. What does the plus sign mean?
that means that these are two different branches of vacua, right? It does not mean that either you're in one branch in which you have a nice space-time description, you're in the other branch, that doesn't make sense as in the background.
The space description that could.
But the string background, so this can be used for, so this story is a story of some flows from a massive theory, right? The flow to the infrared. The only pieces we can use for string backgrounds are the infrared theory. And so we can only use here the HP or the black hole. And there is something funny that happens when we want to go between them. But this cannot be used to construct a string background.
I don't really fully understand what it means, because what does it mean that you have two backgrounds? You started from some nice field theory and you flow to the infrared,
Yeah.
and the Hilbert space splits from distances.
Yeah.
And then what?
Yeah, so if we are in the, let's say we don't flow completely to the infrared, the theory has two branches. One is the linear sigma model, a non-linear sigma model, well, or something like the HP solution. And the other is just a massive.
And there are no operators to take us from one to the other.
No, not in the infrared theory. Of course, in the if you haven't flown all the way to the infrared, then there are.
Well, but in the context of string theory,
And the concept of string theory,
theory
yeah,
was
no.
invented so that you can think of it.
Yes.
What you're really interested in is only the.
Yeah, you're only interested in the infrared, exactly, and only in these pieces where you have the correct central charge.
So what should we make?
Well, as I said, this story with the massive vacuum is a story of the description of the flows and so on in the linear sigma model. The only pieces you can use for constructing string vacuum are these continuous branches that define CFTs, large central charge. And these have no known interpretation in string theory.
If you take it at face value, wouldn't it mean that this computation of the image now uses a criteria whether it's connected or not? Because you start from one side, you vary the parameters, and you end up with something.
Well, so perhaps there are two indices that I've been discussing here. So there is the index of the massive theory, right? The linear sigma model, and that index does not change. Okay. But you get these two vacuum. So that means that the index of purely the CFT and purely the black hole side are changing. That is changing, and that's the one that we were computing here. So we were computing just the index of the infrared CFT.
I think maybe, I'm not sure it's the same as, not this question. Let's say you're like a low energy person in this world, right? And well, someone is twiddling the parameters in the UV theory. You start with a black hole low energy CFT, and they twiddle, and you find yourself in the HP low energy CFT, or you could, right? So,
or you might find yourself in the massive vacuum.
You might find yourself, but let's say you don't. Like,
Yes,
let's say, so isn't that person convinced that these two CFTs are smoothly connected?
So, well, they cannot be. I mean, if they were smoothly connected, the index purely in the CFT should be the same, because it's a property of indices.
I think what he's saying is that varying the parameters as you described, flowing to the infrared, these two operations don't commute. So that if you first flow to the infrared and then vary the parameters, it's not the same as first varying the parameters and then flow to the infrared. If that's the case, then I think it addresses your question.
But you might, I mean, imagine you're like close to the boundary and just make.
This is actually a common phenomenon. Not very common, but not uncommon, where flowing to the infrared and varying parameters don't commute.
Yeah, let me just ask it one more time. Let's say in the UV theory, someone like pretty close to the transition kind of makes a domain wall or something. I mean, or it's something where they just vary the parameters so far away or on one side in space, right? Far away or on the other side in space. Now you flow to low energy. So what does that look like?
So the region near the domain wall would be very singular.
Sure. Okay.
There are situations where you vary the parameters and the answer, the renormalization group can take you very, very far, even though you made small changes.
Yeah,
So imagine you have two coupling constants. You vary one of them, but as you vary these other parameters, it changes from being relevant to irrelevant. It's clear that turning by a little bit and then you vary that, depending on small changes here, it makes a big change.
It's at that wall, it's somehow becoming something bad at that point. Okay.
This doesn't answer the question of what's going on here, but I'm only addressing.
We don't have an answer of what's going on. This is just a description of what happens in the linear sigma model. And exactly what happens to the CFT as you go between one and the other, we don't understand. As I said, we don't have nice models of what could happen. Maybe as you flow to the infrared, some linear. What?
Can it be that it's simply infinite distance? You can't go?
It could be, yeah, could be infinite distance. It is. I think it's that sounds a little unlikely. It could be. It could be that. That could be that you develop a very long throat or some very long vision. That's how normally CFTs examples we know becomes in. But we cannot easily see from the linear sigma model. So in other situations, like for example the conical transition, in linear sigma model, you see a new branch appearing, and you can understand the linear dilaton direction or Liouville-like direction from this new branch. But that's it's a description of what happens with the massive theory.
If we're far from the phase transition, it seems pretty clear that the linear sigma model is trying to flow to HP plus the 2 vector. What is unclear, entirely unclear, is the nature of the transition.
Right. Okay, we're way over time, so there's one little point that I should make. This fact that the index changes and so on is connected also to the fact that the spectrum of D branes is different in the two solutions. So when you have the HP solution, you can have a D0 brane that wraps this direction. And on the other hand, the same config, and that has a mass, which is 1 over G string times perhaps some function of beta, which is non-zero. And then on the other hand, in the black hole case, if you have the same amount of Ramon flux at infinity, you can have that as flux, which is on S2. Okay, it's just a configuration with pure flux, so it's a charged black hole, and that has an extra energy, which is of order 1 in G string. Okay, just the energy of the flux. So that means that as we vary beta, this function should go from being non-zero to being exactly 0. Sort of indication of the transition, and the existence of these branes or fluxes is related to the Ramon ground states, which exist in one case and not the other. Okay. So I think I'll finish here, and maybe I mentioned one little thing, which is that one could also consider charged black holes, so black holes that carry momentum and winding string charge. So you add an extra circle, and then you consider black holes with those charges. And those can be generated by solution generating transformations from the black holes with 0 charges. And the transition that we are discussing here occurs as you approach extremality. So as you approach extremality, the sort of seed solution, which is uncharged, gets very small, and the structural radius gets very small, and then undergoes this transition. It becomes more like a Horowitz constrained solution. And that gives a picture for those extremal configurations in terms of the gaseous strings that are now charged and so on. I mentioned this because this type of black holes were discussed in the past. They had the feature that their extremal limit was singular, and people said a few things about how you could resolve the singularity. But here we're sort of saying a picture of exactly what happens. It's not that you need to resolve the singularity, but that you transition into some other solution, which consists of something that looks more like an oscillating string. Okay, so I think I'll finish here. Thank you.
Seeing that we went a bit over time, let's consider this the end of the talk. Then, so the official end of the talk, but whoever wants to stay and ask more questions.